Welcome to our Chapter 9 problem solving video. In this video, we're going to cover four or five problems from the homework and then the challenge question from Chapter 9. This challenge question will be part of Unit 3 exam, not the upcoming exam or the next exam after that. So this will be on the exam that covers Chapter 9 through 12. However, I find periodic trends and understanding orbitals really helps you understand why certain chemical reactions occur, which often kind of impedes students' learning in these next few chapters that we're going to cover after Chapter 9. So our first problem, I believe, is part of the homework assignment. So if you want to copy it down and turn it in or use it as part of what you turn in, that's a useful use of this session. So we have two emission spectrums from hydrogen. So we have a 410 nanometer wavelength that's given off and a 434 nanometer wavelength that's given off. Remember, energy is inversely proportional to wavelength. So as wavelength gets smaller, energy gets larger. One of these is due to the n equals 6 to n equals 2 transition, so going from the 6th principal energy level to the 2nd principal energy level. And the other one is due from the n equals 5 to the n equals 2, so one less principal energy level or one less valence level it's traveling. Which wavelength corresponds to each one? So this is related to energy. So 400 nanometers is higher in energy, or 410 nanometers is higher in energy than 300 or 434. 300 would be lower than either of them. But 410 is lower than 434, so this has a higher energy. If we're traveling more or from a higher principal energy level to the same principal energy level, or even a lower principal energy level, that's going to be a larger energetic change. Remember, the difference between orbitals gets smaller and smaller as we go higher. But as we go higher and higher, we're just going to larger and larger energies regardless. So since this is a larger overall transition and they're ending at the same finishing point, this isn't the ground state. The ground state would be n equals 1. But since they're finishing both at n equals 2, we can assume that the n equals 6 to n equals 2 is going to be the 410 nanometer, and the n equals 5 to n equals 2 is going to be the 434 nanometers. And we just assign the higher energetic wave to the larger relaxation event. So our next question, 47, kind of a similar question. So according to the quantum mechanical model for hydrogen, which electron transition produces light with longer wavelength? So which one of these transitions will give a less energetic photon or emission spectrum? So we have from the 2p to the 1s or the 3p to the 1s. So we're going to the same position is our final resting state. So we're going down to the ground state, but we're starting from either the 2p or the 3p. Principal energy level is synonymous with increasing energy level. So the n equals 1 is lower than the n equals 2, than the 3, than the whatever. So the 3p orbital is higher in energy than the 2p orbital. Longer wavelength is associated with lower energy, so we want the lower energy transition. So the 2p to 1s transition is going to produce a longer wavelength and a lower energy photon, whereas the 3p to 1s would give a larger energy, smaller wavelength. So just to remind you of this, we had this slide from the lecture. So as we go to larger and larger wavelengths, we have low energy, or we redshift is what some people commonly refer it to. If we go to smaller and smaller wavelengths, we go to higher and higher energy particles. So radio waves and microwaves are very low energy. Infrared is, heat energy, but still relatively low on the, physical sense. Then as we get to X-rays and gamma rays, this is what we would consider ionizing radiation. And so we would call this blue shifting. It's just a general terminology. Blue shifting is making something more high energy. Red shifting is making something more low energy. All right, so for our next problem, we're going to look at problem number 61. How many valence electrons are in each element? This is very simple, although it can be a daunting task. You're never going to have to do this for memorization. Now, if you do a lot of chemistry and you go get a chemistry major, You will want to be able to memorize some of these, especially the first three. The last one, maybe you remember it, maybe you don't. But for our class, you don't need to memorize any of them. All you need to do is use the periodic table. So we're going to simply tab over to a periodic table and find oxygen. So oxygen is number 8 on a periodic table. The number on the periodic table is its number of protons. For the elements, protons and electrons are always equal to each other. So oxygen has 8 protons, so it will have 8 electrons. Sulfur was element 16, so it'll have 16 electrons because it has 16 protons. 16 and 16. If we go to bromine, it would be 35 because it has 35 protons, and rubidium has 37. So if we looked at this, it would have been 8, 16, 35, and 37, because those are just the atomic numbers of those elements. And for the pure element, not the ion, ions will differ by whatever their charge is, plus or minus an electron or however many. But for pure elements, the atomic number or the number of protons is always equal to the electrons. So you just look at your periodic table and you automatically know the answer. All right, question number 65 from chapter 9. Use the periodic table to write down the electronic configurations. So what we want to do is we want to look at the periodic table, find out what its position is in its given block, whether that's the S block, the P block, or the D block for zirconium. Whatever position it's in within that block is how many electrons it has in that orbital subshell. Everything below that orbital subshell is going to be completely filled. What do I mean? So we'll go to aluminum. Aluminum's element 13. So it's going to have the noble gas configuration of neon. Or we could just, write the 1s2, 2s2, 2p6, and then get into our valence shell. Or we can, just abbreviate it as a bracket with neon around it. Aluminum is in the first position of the P block. So its last character in the electron configuration is going to be 1 in the p orbital. Now this is the third principal energy level, so that'd be a 3p1. Everything that comes before the 3p1 orbital is going to be completely filled. And that's going to be a common occurrence for all of these chemicals. So we have the core configuration of neon. We said it was in the first position of the p block. So it's everything that neon had, 3s2, 3p1. If we look at beryllium, we'll go to the periodic table. Beryllium's right here. So it has the previous noble gas configuration. It's in the second position of the S block. So it's in the second principal energy level. So its last chemical symbol is going to be 2s2. There's nothing in that valence shell that comes before 2s2 or the 2s orbital. So we don't put anything. We don't put 2p0. That would just be a waste of work. So our next one is indium. So we'll go look at our periodic table. Indium is down here in the 5th row of the periodic table. So it's at the n equals 5 principal energy level or valence level. And so indium is in the first position of the p block. However, we have d orbitals to consider now. So unlike aluminum, where there were no d orbitals preceding it, now we're going to have to include our d orbitals. Remember that d orbitals are always one principal energy level lower than the valence shell you're in. So at indium, we're in the 5th valence level, or the 5th row of the periodic table. So this is going to be the 4d orbitals, not the 5d orbitals. It's going to be the 5p and the 5s, but it's going to be the 4d. So the last electron in indium is in the first position in the 5p orbital. So that's going to be our last term, 5p1. Everything before that is going to be completely filled. 4d10, 5s2, and then the previous noble gas configuration of krypton. Same thing for zirconium. If we go to zirconium, it's In the fourth group, or the fourth row, or yeah, fourth group, not the fourth row, it is in the fifth row, so it's the fifth valence level. This is going to have the second position in the D block, so we're going to have 2 D electrons. So our last character in the electron configuration is going to be 4D2 because we're in the fifth valence level, and the principal energy level of the D is always 1 lower than the valence level. So we're in the second position. 4D2 is our last character. We're going to have everything completely filled before that. All right. So problem 97, this is kind of the opposite. These are incorrect configurations, and we want to look at finding the correct configuration. This, in my opinion, is actually easier because you don't have to write as much. Well, I guess you do have to write as much, but all we have to do is we're going to add up the number of electrons, and we're going to find that element that has that number of protons, because these are just elements. We're just finding, I didn't say the ion. If I wanted you to find an ion, I would tell you, what the charge of the ion was. It's a +1 ion, it's a -2 ion, etc. From there, you'd be able to adjust from what we're doing. So in this case, we're going to just count the number of electrons. So we have 3, 3, and 9. So that's 15 electrons. We're going to go to our periodic table and find chemical number 15. So that's going to be phosphorus. Now, we could give the correct electron configuration by figuring out, okay, we're in the third valence level. Phosphorus is in the third position of the p orbitals. So my last term in the electron configuration is going to be 3p3. So if we look at that, we have 1s2, 2s2, 2p6, 3s2, 3p3. We could have abbreviated the 1s2 through the 2p6 as the previous noble gas configuration. I just want you to see both ways. The last ones I was showing with the condensed version. These ones I'll show with the expanded version, since we're looking at incorrect variants of the expanded version. So the next one, we're going to do the same thing. We'll count the number of electrons. 2 plus 2 plus 6 is 10, plus 4 is 14. So we'll go to one chemical earlier, silicon. Since we just moved 1 to the left, we can just remove 1 electron, or we can, pretend like we never did the first one and go, okay, we're in the third row of the periodic table. We're in the p orbital, or the p block. We're in the second position of the p block, so my last term is going to be 3p2. My last term is 3p2. Everything before it is going to be completely filled. Just remember how many electrons go into any given orbital. If you forget, just count the block. The s block is 2 across. The d block is 10 across. The p block is 6 across. And if you have to, the f block is 14 across. You can just count these and always know what they are. You don't need to memorize it. Okay, so 1s2, 1p5. So we don't have a 1p orbital. So this has to be a mistake. The p orbital only starts at the second principal energy level, just like the d orbital only starts at the third principal energy level. And the f orbital only begins at the fourth principal energy level. For the last one, we have 1s2, 2s2, 2p8. So we can't have 8 electrons in the p orbital. We can only have 6 electrons. So that's the mistake. I forgot I didn't even go over the answer for this one. So again, we would count the number of electrons. 2 plus 5 is 7. Go to the 7th element. It's nitrogen, and we can adjust accordingly. Again, this one, back to this. There's only 6 electrons that can be carried in the p orbital, so this is the mistake here. We could just add those on and, hope that everything's right and we didn't mistaken, something else for being correct that was accidentally mistranslated. We can just count all of these. If we count them, we get, 12 plus 3. We get the same configuration as we had in the first problem, and it's phosphorus again. So for the last question, very similar to things that we've been doing, but now we're going to work with, very similar to one of the problems for zirconium, actually. They are actually in the same group and have almost the exact noble gas configuration. The challenge problem for Chapter 9, in 2 exams, is doing the electron configuration for a transition metal and giving the orbital diagram of the valence shell. So we can just go to the periodic table, which you'll have access to. Titanium is in the 4th row of the periodic table. In the D block, it's the 2nd element in the D block, so its last orbital term is going to be 3d2. Not 4d2, because this is the first D row of D elements, or D block elements. And so we start at the 3D. We start at 2p and 1s, 3d, 4f. Just something that we have to remember. So this is going to be the 3d2, and everything before that is going to be completely filled. If you want to use the previous noble gas configuration for a condensed formula, totally fine, less work on you. If you forget that, you can just put all of the orbitals in their subshells that come before the valence shell, or the last valence electron, which has kind of been the focus of this video, is finding where your last valence electron is. If that's your last one, every one that comes before it has to be there. The orbital diagram would be something like this. We can go over a couple different ways to do orbital diagrams. If you're giving me an orbital diagram, I want it on an energy landscape. That means that you lay out the orbitals such that as the energy increases, so does the vertical height of its position. So the 4s should be below the 3d, which should be below the 4p. Now, I just copied this from the textbook and didn't crop it. Since I asked for the valence shell, I would only want you to show the 4s and above. Whether you decided to show the 4p's being totally empty is up to you. It is correct, but it's a little redundant. In the case of an electron configuration, we don't show redundancy. For the sake of an orbital diagram, we do orbital diagrams to be very specific about what's going on with the electrons. And so designating that there's an entire empty subshell is a valid thing to do, although not required. So for the challenge question, you would just have to do the 4s with 1 spin up electron, 1 spin down electron, slightly lower in vertical height than the 3d orbital, which would have 3 empty d orbitals and 2 partially filled orbitals with the same oriented spin. Whether they were both spin up or both spin down doesn't matter. They just both have to be the same direction. And that's the challenge question for Chapter 9. If you have any questions about these, make sure you reach out to me, and I'll see you in class.